Yes, sir. We are going to, with the name of Allah, I'm going to recite some verses from the Holy Quran. أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. إذا جاء نصر الله والفتح ورأيت الناس يدخلون في دين الله أفواجا وسبح بحمد ربك واستغفره إنه كان توابا. صدق الله العلي العظيم. I'm really very grateful to Dr. Muhammad Imran. He is an associate professor and a dean of student affairs in GIK, and he is also associated with the Department of Material Science and Engineering in GIK. I'm really very grateful to you for sparing time for the University of Engineering Technology, especially our metallurgy and materials final year students. I'm also looking forward some master's students and one or two PhD students will join shortly. So, sir, I welcome you here and over to you, sir.
Thank you very much, Dr. Saab. It's really a pleasure and an honor for me to give a presentation or a seminar or lecture, whatever you can call it, in front of all of you. Let me introduce myself. I am Dr. Muhammad Imran Khan, and I'm working as Associate Professor and Dean of Student Affairs Department at GIK Institute. And my parent department here in the institute is Faculty of Materials and Chemical Engineering. I did my doctorate from Tsukuba University, Japan, from Professor Miyazaki and Kim Lab, which is known for its groundbreaking research in smart materials, and particularly titanium nickel based smart materials. We have got also here in GIK Institute facilities where we are currently doing research on titanium nickel, titanium based and T and Z based alloys, mainly for biomedical applications. So my today's topic is I will start sharing my screen. Please let me know that whether you can see my screen on your screens or not. And Dr. Will we record that?
Yes, sir.
That lecture?
I'm going to record. Yes, sir.
Okay, thank you. Right, so I'm going to share my screen now. So I hope now you can see my screen in front of you, right?
Yes, sir.
Okay. My today's talk is about the applications of titanium nickel based smart materials for biomedical, mainly for biomedical application. I have already introduced myself. Basically, first we need to understand what are basically biomaterials. Biomaterials is a wide-ranging field, and it basically encompasses the aspects of basic biology, medicine, engineering, and material science. So we can expect a very nice fusion of all these disciplines. And at the end, we get a very useful outcome in the form of biomaterials, which are responsible for the quality of life in the patients who unfortunately go through a very painful, period of their life because of any incident or accident. It can be a disease, it can be a very horrible accident, and where you can expect the breakage of bones, and sometimes bones are broken in a way that their natural healing is not possible. So we need to intervene, and we need to replace either the whole part of the bone or only a partial portion of the bone with suitable materials. And those materials, they are basically termed, or they come in the category of biomaterials. And according to a consensus decision by a panel of experts internationally, we can define a biomaterial as it is a material which is intended to interface with biological systems to evaluate, treat, augment, or replace any tissue, organ, or function of the body. And we can get numerous examples of biomaterials or bioimplants. You can see on the screen in front of you uh, some examples of bioimplants. So on my left hand corner, upper corner, you can see a bioimplant which is known as artificial heart valve. Then beside it, you can see vascular grafts, artificial vascular grafts. Then we can see here the screws and clips and many small components which we need to insert or place inside the human body during different procedures, during different surgical procedures. Then you can see here the application of an artificial vein graft, which is placed to bypass the passage of blood flow in an artery. Then very well-known example of a total hip joint replacement. And we can see that here in this particular example of hip joint replacement, you can see the application of all three major classes of material. For example, the metallic part, the plastic cup belongs to polymers, and then coatings of some ceramic materials along with metallic components which directly is inserted inside the remaining bone part when we replace the natural or broken total hip joint in the patient. Normally, this hip joint problem comes in elderly people, and we know that when it happens, the poor people, they go through a very painful period because of this broken part, essential part of the body. And if it is broken, the only remedy is which is sustainable is to replace the natural hip joint with an artificial hip joint. So we call it total hip joint replacement. And there we need very specialized materials. And those materials should be biocompatible, should be non-toxic, should be inert, and they should have good osseointegration, which is a property which we need when we try to insert a foreign material inside the body and which is directly in contact with the bone. Different then you can have the example of intraocular lenses, and we know very well about this application. Mainly we are talking about the polymeric materials, PMMA, polymethyl methacrylate, acrylics or silicones, which are used to make these intraocular lenses, which normally we place after the cataract operation, which is a very common problem. We will not consume our time on these applications because our main focus is on the titanium nickel based, the applications of titanium nickel based materials. Then you can have the examples of dental implants. So a range of dental implants are available in the market. And when we talk about dental implants, so we can start with the arch wires, the permanent fixing of artificial teeth inside the jaw bones of the humans. And again, we can imagine very clearly that when you are putting a foreign material inside the mouth of a human being, then that material should be essentially biocompatible. It should be non-toxic. It should not leach the poisonous ions or atoms or molecules inside the mouth, which can mix in the saliva, which can go inside our stomach and can create many complications which can lead to very painful condition for the. Then we can have another area where we need certain kind of medical tubings, then catheters, and then stents. So these catheters or medical tubings, they are used in various surgical procedures. Whether you talk about the 100% invasive surgical procedures or minimal invasive surgeries. You may be aware of the procedure which is known as angioplasty, and that angioplasty procedure basically is related to open the partially clogged or blocked arteries or veins, uh, which can treat the problem of heart attack, right? Previously, the only option which was available was the bypass surgery. Bypass surgery is in the past, it has been a very invasive, intensive surgery. But this procedure of angioplasty, it is related to the field or the broad area which is known as minimal or minimum invasive surgical procedures, where we just enter a small stent through our veins or arteries, which can be placed by pushing these stents through a special guide wire, and we can place these stents on those places where those arteries are blocked, and that can save the patients from going through a very intensive bypass surgical procedure. These catheters, they are used inside the human body in order to do many tasks. For example, these catheters are, as I told you, these catheters are used to place the stents. They are used to retrieve the stones from various parts of the body, like kidney, like gallbladder, and they can also be used as non-kinking wires, which are used for many minimum invasive surgical procedures. If we talk about these synthetic biomaterials, so basically we are talking about almost all kingdom of material available with us on this planet Earth. For example, if you talk about metals, so metals are mainly used for dental implants, orthopedic screws or fixation. If you talk about polymers, then you can get the example of application of drug delivery devices. Then skin, the treatment of skin damages. Then ocular intraocular implants, which we place after the cataract operations. If we talk about ceramics, then again bone replacement, where hydroxyapatite is one of the major candidate material for the bone replacements. Then heart valves, dental implants. If we talk about semiconductor materials, then you can think of biosensors, implantable microelectrodes, which is used for normally pacemakers type of application inside the human body. So all these materials, they are on the table in front of us to be used as biomaterials or bioimplants in order to either save the life or you can talk about the improvement in the quality of life. So that is why this field of biomaterial is one of the fastest growing fields on this planet Earth. If you talk about the in terms of economical terms or in terms of engineering sector. Basically, these are the requirements of biomaterials. Any biomaterial is desired to be inert or specifically interactive with the inner environment of the human body. It should be biocompatible. It means that biocompatibility means that your body should be accepting that particular bioimplant. Then it should be mechanically and chemically stable. You can think of that if we place, for example, a titanium nickel or titanium based implant to replace a bone inside the body, and if it is not mechanically stable, then the first thing which we will encounter is the failure, structural failure inside the body. Then it should be chemically stable, means it should not be reacting with the physiological fluids which are present inside the body. Then we may be having a requirement of biodegradability, means that we may be desiring a bioimplant or a biomaterial to stay inside the body for a specific period of time, then it should be removed. The current available options are either we use a biodegradable material or we need to go through a second surgical procedure, right? But it depends upon application to application, that whether this biodegradability is required or not. Then the material should be processable, means because when we talk about the biomaterial, the bioimplants, so we may be talking about very intricate shapes. So it means that the available manufacturing processes, they should be able to be applied on those materials. You should be able to give the desired shapes and desired other characteristics to those available materials. Then the material should be non-thrombogenic. Specifically, when that bioimplant is constantly in contact with blood. Because non-thrombogenic means that it should not be creating any blood clotting. Because some materials, they can induce the effects when they come in contact with the blood, they start creating blood clots. And those blood clots in arteries or veins, they can be fatal. They can lead to heart attacks, they can lead to strokes and many other complications. Neuropathy is another problem which is there because of this problem of thrombosis. Then it should be sterilizable, means the surfaces of those bioimplants, we should be able to sterilize them. Sterilization is a process in which we kill all the pathogens, we kill all the undesirable germs, bacteria, viruses, or any kind of undesirable microbial species. Now you can see this is the global biomaterial market. You can see that here from 2019 to 2027, the forecast is that we can expect a jump from $109 billion to $328 billion in terms of this global biomaterial market. And all the indicators, they are indicating a steady increase in the coming future in the field and industry of biomaterials. So our material engineers who are planning to develop careers in this particular field of material engineering, then it is my strong suggestion that this area of biomaterial is one of the promising area, and we are expecting quite a significant number of job opportunities and business opportunities in this area. Now this is a list of those devices which are currently in the market. You can talk about incontinence supplies, home blood glucose monitoring products, wound closure products, implantable defibrillators. These defibrillators are similar to pacemakers, but with a difference that they can apply a relatively higher level of electric shocks to the heart in order to in order to start the heart again. Because in some physical problems or some because of some specific diseases, it is an issue in those patients that their heart can stop without any indication. So those defibrillators, they are placed inside the body just like the pacemakers, And when those devices, they sense that there is an abnormal, stopping of the heart, so they, start, electrifying the heart in order to revive it. Then soft contact lenses, orthopedic fixation devices, mainly for the treatment of broken bones, pacemakers, examination gloves, which is a routine usage, item. Then interventional cardiovascular coronary stents, which are known as stents, cardiovascular stents. Then arthroscopic accessory instruments, prosthetic knee joint implants, lens care products, prosthetic hip joint implants, multi-parameter patient monitoring equipments, mechanical wound closures, wound suture products, which is used to basically, close the wounds, either out at the skin or inside the body, after a very thorough and detailed surgical procedures. Then absorbable polymers, hearing aids. Then we come to wheelchairs, scooters, or mobility aids. Then peritoneal dialysis sets. That is another very important area where the biomaterials or bioimplants are playing a major role when we talk about the dialysis types of application. These are 10 medical device trends which we can expect that starting from 2023, they can be the focus of this area of biomaterials or biomedical implants. And these include the wearables, medical robots, immersive technologies, 3D printings, Internet of Medical Things, 5G technology, medical waste management, then MIDs or minimally invasive devices, cybersecurity, and artificial intelligence. Now, basically biomaterials, as I already told to you, they fall into one of these three categories: metals, ceramics, and polymers. And if we talk about metals, then in case of metals, you can have cobalt chromium alloys. Their applications you can find in artificial heart valves, dental processes, orthopedic fixation plates, artificial joint components, and vascular strands. If we talk about gold and platinum based metals or alloys, then we talk about basically dental fillings, electrodes for cochlear implants. If we talk about silver tin copper alloy, then we are basically talking about dental amalgams. If we talk about stainless steel and mainly 316L stainless steel, then we are talking about dental processes, orthopedic fixation devices such as plates and screws and vascular strands, and then titanium alloys, also including titanium nickel based alloys. Then we are talking about artificial heart valves, dental implants, artificial joint components, orthopedic screws, pacemakers, cases, and vascular strands. So these are the brief applications of these metals and alloys. These are the mechanical properties of these common alloys. For example, magnesium alloys, if you talk about Young's modulus, then it comes in the range of 41 to 45 gigapascal, and its UTS or ultimate tensile strength, it is in between 65 to 258 megapascal. If we talk about pure iron, then we are talking about 205 gigapascal of Young's modulus, and then UTS is about 245 gigapascal. Stainless steel, about 189 to 205 gigapascal, and its UTS is 620 to 690. They have got 105 to 125 gigapascal of Young modulus, and 750 to 1200 megapascal UTS range. Cobalt chromium alloys, 240 to 900 to 1540 megapascal. So if we talk about these sterics on stainless steels, titanium based alloys, and cobalt chromium alloys, so basically these sterics are there because these categories are non-biodegradable metallic implants. And if we talk about magnesium alloys, so these are the biodegradable materials. Pure iron we do not use inside the human body, and this is the young modulus of natural cortical bone, the bone which you can find in the upper part of our leg. So its young modulus is in the range of 3 to 30 gigapascal, and its UTS is 130 to 180 megapascal. So the real problem which is here, that real problem is that there is a big mismatch between the Young's modulus of natural bone and our available options of materials or biomaterials, which we can replace as the partial portion of the bone or the whole bone. The problem with this difference in Young's modulus is an effect which is known as the stress shielding effect. This stress shielding effect is there because when stress is applied during the normal day functions of a human body, and you have already implanted a metallic implant to replace a bone, for example, so then that stress which is simultaneously applied on the metallic implant and the remaining part of your natural bone, then you can expect that because of difference in Young's modulus, the metallic part will be elastically deformed differently, and the natural bone part will be elastically deformed differently. So that will create very painful conditions, and your remaining part of bone, they can be deformed because of this stress shielding effect. So one of the goals of current research in case of these in the research of these biomaterials, bioimplants, specifically in titanium nickel based alloys, is to reduce the Young's modulus in order to match their Young modulus with the natural bone. Okay. Now we talk about our material of today's talk, that is known as nitinol, and that is basically an alloy of titanium and nickel. That nitinol is a titanium-based alloy that can be used in a wide range of applications, including engineering applications and biomedical applications. It has got two properties, mainly two properties. One is known as superelastic property, the other one is shape memory effect. Now, if we talk about superelastic property of this nitinol, so then basically it is a property that because of which the material can return to its original shape after a significant amount of deformation. I can give you the example of polymeric elastics, like rubber band, for example. So all of you must have seen the rubber band. So if we apply some stress on the rubber band, so you can stretch it to, significant strains. And when we remove the stress, those elastic bands, the rubber bands, they come back. Exactly same thing happens in case of nitinol. You can, if you apply high level of stress, they can be stretched to large deformation strains. If we talk about normal metals and we induce the same amount of deformation, so then we enter basically into plastic deformation region, and that deformed metal is not returnable. It stays there because plastic deformation has happened. But in superelastic material like nitinol, you can apply stress, you can achieve significant deformation, and when you remove the stress, they can come back just like rubber band. And this property makes it ideal for medical devices that require large recoverable deformation, such as cardiovascular and gastrointestinal stents. Right? Now, if we talk about those nitinols, basically we can change the relative amounts or relative compositions of titanium and nickel. Normally, when we talk about superelastic nature of these materials, so normally we talk about slightly nickel rich titanium nickel based alloys. And if we compare the elasticity of this titanium nickel or nitinol alloy with stainless steel, it is 10 times more than the nature elasticity of the stainless steel, right? And because of this property, these nitinol stunts, they can conform to and deform with blood vessel wall without damaging the surrounding tissue. It means that you can place these stunts very comfortably at the desired locations inside the human body, and this process is done without opening any, without doing any major scar, without doing any major surgical procedures. We just need to insert these stunts from any vein or arteries, either from our arm or through our leg. And then we can push these stunts to reach their desired positions. And another characteristic of the nitinol is known as shape memory effect. It means that they can remember their shape. Means if you deform them, apply stress, deform them. When you remove the stress, the material will be in the deformed shape. And then when you heat it, the material will come back to its original shape. That is why it is known as shape memory effect. And both superelasticity and shape memory effect, it is due to a martensitic phase transformation, in which austenitic phase is converted into martensitic phase, either because of the application of stress or because of the usage of heating or increase in temperature, right? And the martensitic transformation, which is induced due to the application of stress, in case of superelasticity, the martensite which is formed, it is known as stress-induced martensitic transformation. Now, this superelasticity is also known as pseudoelastic effect, which happens when your titanium nickel alloy is in austenitic condition. And shape memory effect, which is known as SME, or one-way shape memory effect or two-way shape memory effect, it happens when your material is in martensitic condition. And we can, now you can see here, this is the schematic diagram where you can see the schematic of the principle of shape memory effect. Doctor, please let me know when this session is about to finish, क्योंकि वो फिर हमें दूसरा Zoom session start करना पड़ेगा. जी जी. Now I was talking about this shape memory effect. So initially, when your material is in the martensitic form, we can have a self-accommodated martensite. When we apply stress, so these twins or self-accommodated martensite is converted into single variant martensite. And when we heat it, it converts into austenite. And when we again cool it, it regains its position or its shape. For example, if you see this schematic diagram, there you can see your initial material in the martensitic form. Initial material in the martensitic form, we apply stress, we bend it. When we remove the stress, the material remains in the bent form. And when we heat it, it again comes back to its original form, and you again get this straight rod. And this is not only for the straight or bending position. You can make any shape, any intricate shape, and that material will remember that shape. You deform that shape, you heat it, and then it will again regain the shape. For example, if you have got a titanium nickel based wire and you make a star using that wire, and then you deform that star or the shape which you have made, then again when you will heat it, it will again become in the form of that star shape. So that is basically the shape memory effect. That is why we say that this shape memory alloy, it has got the unique ability to remember a shape which we can memorize them, right? Any shape can be made memorized by these titanium nickel based materials, and they regain those remembered shapes after deformation at specific transformation temperature. And those transformation temperatures, they are known as martensitic transformation temperature. And the shape memory phenomenon, basically, it is based upon a solid to solid martensitic transformation. And we know, or we all, because we belong to the same domain of materials engineering, we already know what is a martensitic transformation. I will not go into the details of these martensitic transformations. And the other thing is that when we talk about that these materials, they can regain their remembered shape at a particular temperature. So then the question should be coming to our minds that what are those temperatures? Are those fixed temperatures, or we can alter them? So the good news is that we can change those transformation temperatures according to our desire. For example, if you want to start the shape memory effect at 40 degrees centigrade, we can do it. If you want to have the shape memory effect at 50 degrees centigrade, we can do it. If you want to do it at 60, 70, 80, 100, 200, 300, 400, we can do it. And how we can do it? By altering the chemical composition of the alloy. Now, this is a live demo. Can you see this video? All of you? Can you see this video? Doctor, can you see this video, in front of you?
जी sir, मुझे नजर आ रहा है.
Okay, so you can see a very nice, practical application of these shape memory materials. This is basically a shape